Okay, good. So hello, good morning from Netherlands. Unfortunately, I couldn't make it to Tromsø. I've been there once before. It was a magnificent place, and hope you're all enjoying the spectacular views there. So my name is Beert Wouters, and together with Martin Sharp and Gabriel Wolken, we looked at melting of Arctic glaciers and ice caps and their impact on sea level. So we looked at the glaciers and ice caps which are disconnected from the ice sheets of Greenland and Antarctica, so the smaller mountain glaciers and ice caps in the Arctic region. So these glaciers, they form in regions where more snow accumulates than the atmosphere can melt in summer. These ice bodies will start to grow and the ice will start to flow to transport the ice to lower elevations until a very fragile equilibrium is reached between accumulation and ice melt and ice calving for those glaciers ending into the ocean. So in fact, these mountain glaciers are just, mountain glaciers and ice caps are just miniature versions of the ice sheets of Greenland and Antarctica. So what makes them so interesting? Now, if you look at the potential sea level contribution from the ice on our planet, we see that Antarctica holds about 60 meters of potential sea level. So if Antarctica would totally melt, sea level would rise by 60 meters. Then there's Greenland, about 7 meters. And the glaciers only hold about 32 centimeters. So that's a very small contribution compared to the ice sheets. So you could say that you might think there's no reason for immediate concern, maybe. So let's have a look at what happened in the past. We know that between 1993 and 2015, sea level rose by about 3.1 millimeters a year. Now, this is a slide that I show to my students at university, and I ask them to assign the right label, so the right label to the right color in the pie chart here. And I'll give you a few seconds to do this exercise for yourself. And what's most of the time surprising to my students is that, in fact, these mountain glaciers and ice caps, they contributed more to sea level rise than Greenland and Antarctica. So 0.7 millimeters a year compared to 0.6 millimeters for Greenland and only 0.25 millimeters a year for Antarctica. And if you look at the longer term, the contribution is even more spectacular. So in the 20th century, they contribute most of all components to sea level rise. So 0.6 millimeters a year compared to 0.35 millimeters a year for Greenland and only 0.06 millimeters a year for Antarctica. So they definitely can't be neglected. So they had a very strong contribution to sea level rise in the past, but what about the future? So this here shows these sea level projections from the latest IPCC report. We see that between now and 2100, you can expect the sea level rise of about 43 meters to 0.84 meters, or 0.43 meters to 0.84 meters, depending on the pathway that we follow. And so depending on our actions in the future. From this, thermal expansion is expected to contribute most, somewhere between 10 and 30 centimeters. But then second, are the mountain glaciers with a contribution of 10 to 20 centimeters, and only then Antarctica and Greenland appear. Now, I don't want to downplay the importance of these ice sheets because there's still many processes that we don't fully understand there, especially in Antarctica. But these smaller glaciers definitely shouldn't be forgotten. So that's why we looked at them in our study, and we focused on the glaciers in the Arctic region. So we looked at the glaciers in Alaska, Arctic Canada, the Russian Arctic, Svalbard, Iceland, and Scandinavia. So that's about 80,000 glaciers. We have about 215,000 glaciers worldwide. So 40% of all glaciers are located in the Arctic. They cover an area of about 430,000 square kilometers. So 62% of all the glacier regions outside of Antarctica and Greenland. And they hold about 100,000 cubic kilometers of ice. So that's about 63% of all glaciers on Earth. That's equivalent to about 22 centimeters of sea level rise. So there are many glaciers in these regions, and they are located in probably the worst possible location. If you probably all know that the Arctic is the fastest warming region on our planet. And you see a warming which is 2.5 times faster than the warming on the Northern Hemisphere. with a rise of 3.1 degrees Celsius since 1961 in the cold season, 1.8 degrees Celsius in the warm season. So this is the surface temperature, but also the oceans are warming, which means that these glaciers, they're under attack from both above and below. And the future doesn't look any better, of course. We can expect a warming of more than 4 to more than 7 degrees in the Arctic, depending on our actions within the near future. So how do the Arctic glaciers deal with all this warming? Well, not great. They're not doing great at all. These are field measurements, which go back to the 1940s. So in Arctic Canada, Iceland, Svalbard, Northern Scandinavia, and Alaska. And we see that on average, the glaciers, they lost about 20 meters in elevation since the 1950s. And that's the Pan-Arctic average. But for example, Alaska lost more than 35 meters since the mid-1950s. So it's not looking good, and actually some glaciers have already disappeared. Now these measurements, they're based on, they're made in the field. They're made by putting stakes in the ice and then returning the next year to measure how much ice was lost. So this is a very labor-intensive activity. It's not easy to get there. There are many challenges that we have to deal with when doing that. The Arctic definitely isn't the most welcoming place to visit. You have to deal with crevasses, so these cracks in the ice which you need to cross. Some of them are easy to spot, these are easy to spot, but sometimes they are buried under snow, and that's a great risk when crossing them because you don't see where they are. You have to deal with avalanches. There are polar bears which may attack you, but they also may run over the stakes, so destroying your measurements. And something that we see happening more and more often is that meltwater streams are cutting out the access to the field location. So it's a very challenging activity. And all in all, we have only 27 glaciers where we have long-term continuous measurements. These are shown here in the black dots. So 27 over the entire Arctic. And they're mostly located in easily accessible locations at low elevations near the coast, so easy to travel to. And the question then is, of course, are these 27 glaciers, so this rapid decline that we saw in the previous slide, is it really representative for what's happening to all of these 80,000 glaciers in the Arctic? And for that, we looked at satellite data. And we used the Gravity Recovery and Climate Experiment. So that's a European-US mission. Actually, it consists of 2 missions. The first one flew between 2002 and 2017. And now we have the GRACE follow-on mission, which was launched in 2018. And they consist of 2 satellites, which you can see here. And the concept behind this mission is actually very simple. So it consists of 2 satellites in the same orbit, so they travel behind each other and are separated by about 200 kilometers. And they're not directly measuring changes in the gravity, but they're tracking the changes in the distance between the satellites within 1 micrometer. So that's 1/100 of a human hair. So what happens if you look at the upper plot here? So if these satellites approach a mass body, for example, a mountain here, this first satellite will experience more pull from this mountain because gravity is inversely proportional to the distance to a body. That's Newton's law, which means that this satellite will be attracted more to the mountain than the second one because they're separated by 200 kilometers. So the distance between the 2 satellites will change. That's what's being measured. Once the first satellite crosses the mountain, the second one will be pulled towards the mountain, which means that the distance between the 2 satellites will change again. So continuously measuring these distance changes allows to retrieve the gravity variations at a very small scale in the order of 10 to the -8 meters per squared second. So that's 1 billionth of the gravitational attraction that we experienced on Earth, 9.81 meters per square second. And at short time scales, if you look at time scales of decades, these changes in gravity, they're mostly related to how water is moved around on the surface of the Earth. If an ice body melts, For example, if Antarctica melts, that means that there's locally less mass than before, so the gravitational attraction at this location will be lower than before, and that's what these satellites measured. That's also shown here. So this shows the changes in surface water load on Earth. So expressed in an equivalent water thickness. And a blue color means that there's more water at a certain location than the long-term average between 2002 and 2019. You can see that this changes in time. So there's a lot of seasonal activity around the equator. But if you look at the Arctic regions, you may have noticed that they were blue at the start, but near the end of the observations, they become more and more red. And red means that there's less ice present in these locations than before. And we see this in Greenland and Antarctica, but also in these Arctic glaciers that we were studying. So in the northern Canada, the south of Canada, polar Canada, Alaska, Iceland, Svalbard, and the Arctic Russia. So in all locations that we study, we see a negative trend in mass, in ice mass. Now, if you sum all this mass together for these regions, we get this plot here. And this shows a cumulative ice mass loss since 2002 in cubic kilometers. If we consider the Arctic as a whole, so all glaciers in the Arctic, not accounting for Greenland, we see that these glaciers, these mountain glaciers, they lost 400,000 cubic kilometers over the past 20 years. And so that's almost impossible to imagine 4,000 cubic kilometers over 20 years. We see that Alaska contributed most. That's because Alaska is the largest ice body in the Arctic. And then second comes the Arctic Canada, but also Iceland, Svalbard, and Arctic Russia, they contribute a lot relative to their size. If you take the mass loss relative to the size of the regions, actually Iceland contributed most or melted fastest over the last 20 years. And altogether, this was enough to raise global sea level by more than 1 centimeter over the last 20 years. So to summarize, our measurements, independent of which measurement you take, whether it's field measurements or satellite measurements, not only GRACE shows this, but also any other satellite measurements of the Arctic glaciers shows that there's rapid and ubiquitous melt in this region. They contributed more than 1 centimeter to sea level rise over the past year, over the past 20 years. And we also see, if we look at long-term measurements, that the ice loss in the region is increasing. Now, we already committed to some future warming, but we should do everything we can to avoid any more warming, because that would be dramatic for the Arctic glaciers. So the future totally depends on the actions that we take now and in the near future. And with that, I would like to conclude, and I'd be happy to answer any questions. Thank you.
So I open up to questions.
I have a comment, if I may, Terry.
Yes, of course.
Yes, yes, sorry, I should introduce myself. So my name is Margareta Johansson, and I'm the coordinator of Interact. I was just wondering if you were aware of that we have been collaborating with a company called AFRI, and they have developed drones, because you were mentioning the hassles with walking on glaciers with the crevasses and of course all the molines and everything. And they have developed or at least tested out a sensor that measures the mass balance stakes at Tafela in Sweden. And they did it with the same precision as when you do it by hand, walking out there, just to sort of try to use drones and minimize the risks. And that is something that you can find on our website under there is a drone section. So if you're interested in that, then you can go there and have a look what they have developed.
Yes, thank you. I wasn't aware of that, but I would definitely be interested. To save a lot of hassle while we're getting there.
It
yes.
might be that we need to do that in the accumulation area. Maybe you can see where you're going in the accumulation area, but sometimes in the accumulation area.
Yeah. But of course, you still need to get there to put the drone on the ice, I assume.
Of course.
If you can solve that problem, that would be great. But this would be the first step.
But I want to come back with a comment rather than a question. And that is this morning, we made a contact between two people here, Mario, and who's looking at could look at the erosion inside places and ice sheets. And Piotr from Holmsund in Svalbard, who has been looking at caves, big caves inside glaciers. And I have begun to get frightened that we might be underestimating what could happen to our glaciers if we don't look at inside, what's happening inside, because we could have collapses that we can't predict just by looking at the surface of the glaciers. So I think that the whole of this meeting is about collaboration and about synthesis. And I would really advise you three to get together to talk about whether we could be coming up with a dramatic change that we are not predicting, we're not even looking at. And I had personal experience of the collapse of glaciers in northern Sweden, which weren't predicted. They were just collapses, but there were collapses around ice caves. Simply the roof of the ice caves became too thin, and then a big area of glacier just disappeared, collapsed and disappeared. So I would like to make a suggestion that you three keep in touch and try to refine projections based on what could be happening inside the glacier, as well as on top of them.
Thank you, Terry. Of course, we have very good data from more 120 years, because the first mapping area prepared the Swedish-Russian expedition on the 120 years ago, and we are collected still many photo area, picture, and also all maps. And now we have made some film how changes this area from the last 120 years, because the few glacier also advanced and retreated again. And it's very important places on the world, because our forecast is from the next 20, maybe 30 years, the fjord will be open, because the glacier inside of the fjord completely disappeared. It's also one element from the station for the better cooperation, checking how fast going the process. In this part of the Svalbard region, because this is places where we have the two current, low temperature current from the Barents Sea and hot flux temperature on the west. This is quite good for the observation and changing the data between our partners.
Thank you very much, Piotr. I don't know whether you want to comment.
I totally agree with your commentary. We can see a lot from space and from in the field, but what we actually measure there is the outcome of the internal processes, which we don't measure from space. So we really need to get together as a community to understand all of this, bring all the data and observations and ideas, theories together to come to a better understanding.
Please keep in touch with Hannele about ways of keeping together, because we can fund transnational access in the future, we hope. So please and we have other mechanisms too. Sorry, Mario wanted to respond.
Yeah, it's part of the big problem how to correlate remote data with in-situ measurements in the first place. So it's a big problem everywhere in environmental science. This is one part of it. But another more special case where I think, especially when it comes to escalating effects that need some attention, pressure channels inside the glaciers versus escalation points could happen. And also glacial lake outbursts. For example, last summer we were studying in the North Sea glacial lake development and its outburst into the fjord. And these are the places where suddenly have a lot of metaphor, which could lead potentially to glacial instability. And maybe when we join our forces, we could get more information about such extreme events
Thank you, Maya. And I'm just going to add one more comment. So please forgive me, I'm dominating this discussion a little bit. But I know from a massive mega inland tsunami in southern Siberia where I work, that what happens when an ice dam breaks can be absolutely devastating for human life, for biodiversity, for whole landscapes. And that happens very, very quickly. And of course, the driest period, as I understand, was created by the breaking of an ice dam in the Yukon area. So if we don't understand these rapid processes that could happen from what happens inside the ice, we could be facing catastrophes that we can't foresee now. So I would encourage you three to talk together. But thanks again, Beert, for your very stimulating talk. Many thanks.